Hi, Dr. Bettina Heinz back with you again for another exciting episode in chemistry. We are concluding our gas chapter today with the fourth episode, part 4. And these are the topics that we will talk about. We will talk about molecular speeds. That means how fast molecules fly around in space. Energy distribution curves, the Graham's law of diffusion and effusion, gas mixtures, Dalton's law of partial pressures, what vapor pressure is, meaning liquid pressures or liquid vapor pressures. We're basically dealing here with water vapor, collection and isolation of gases, the downward displacement method of gas evolution. In the pneumatic trough, we will have an experiment that will be shown to you at another episode that will be aired, and the relative density of gases. Distribution of molecular speeds, very important. We have molecules that are constantly flying around. They're whizzing past my head right now. Carbon dioxide, oxygen, water vapor, hydrogen, nitrogen, helium. They're constantly whizzing past me, colliding with me here and there, but it doesn't hurt, they're so small. So depending on the temperature and the pressure, of course, we will have different speeds. Now the molecules are just like people. We have some slow pokes, we have some real fast ones, but we have an average speed of the molecules or the particles. So this is what we call the distribution of molecular speeds of gases. So the higher the temperature, the higher the velocity is of the average. So everybody is accelerated a little bit. So the average kinetic energy of a gas at a certain temperature is governed by 1/2 mass times velocity square. And this means the average velocity, and this means the average kinetic energy. So this relationship was established by two important people, Maxwell and Boltzmann. Boltzmann had a hard time in being accepted by other scientists, and he committed suicide in Austria. So things don't always end well, but now, of course, this law is called the Maxwell-Boltzmann distribution law of kinetic energies or velocities of molecules. So what they had established is that at a given temperature, we have a certain distribution of average energies or average speeds. So we have here at a given temperature an average kinetic energy, which is here at the peak of the curve. And this is the number of molecules that have that kinetic energy. Or you can substitute the kinetic energy with velocity when we have the same mass of the particles. So we're looking usually at one type of gas at a time. So we can correlate velocity with kinetic energy directly. So notice there's a little interesting trend here. That means at lower temperatures, more molecules will have the certain average kinetic energy than at higher temperatures. And that at higher temperatures, the curve flattens out. So there is a more widespread display of various speeds. The average is still at the peak of the curve, and notice that there's no upper limit to the maximum speeds. So the curve sort of tapers asymptotic off here on the right. So the red T is smaller than the green T. Green T, didn't mean to say T, but it's here the temperature. And here is the black T, the black curve that is more flattened and more spread out. Now, how can we determine the actual speed of a molecule at a given temperature? Let's look at carbon dioxide. let's say it's a normal room temperature of maybe 25 degrees, normal atmospheric pressure of about 740 millimeter mercury, or 760 if you prefer, then most of the carbon dioxide molecules will have a certain speed. Some will be very fast, some will be slow, but most of them will have the average that we have seen in the curves. We can determine that by the following formula. Like U is here the molecular speed, and that is according to the root mean square molecular speed law, RMS we often refer to that, root mean square. So we have the mean velocity of the carbon dioxide molecules. Square root is 3 times the universal gas constant times the absolute temperature. So we would have to take 25 degrees plus 273, which is 298, divided by the molar mass. And the molar mass of carbon dioxide is, carbon is 12 grams per mole. Oxygen each is 16, so it's 32 plus 12 is 44 grams per mole. And then you plug in these values, and then you know the average speed of the carbon dioxide molecules. They use another R constant here. They use 8.31. The units are, in this case, kilograms times meter square over second square times Kelvin times mole, because that then lets itself be worked with the other dimensions much better. Remember, the units have to cancel in an appropriate manner, and we have to end up with meters per second, right, which is velocity. Here we have some comparison of the various molecular speeds, average molecular speeds at 25 degrees in meters per second, computed by Maxwell, James Clerk Maxwell, who lived from 1831 to 1879. Wasn't that old when he died, but did a lot of important work for science. So we have here the average speed. Sometimes they use V or sometimes U, meters per second. So hydrogen, a hydrogen molecule is by far the fastest. It's the smallest gas molecule. It has a molar mass of 2 grams per mole. It's a diatomic molecule, diatomic gas. So when we look at the root mean square equation, then you know the molar mass is very small. So that means, of course, we can expect a high average velocity of all the hydrogen molecules. A second, close second is helium, but it has 4 grams per mole. So this component is going to be higher, therefore the value is going to be lower for the velocity. We haven't all the gases here, but notice that water vapor is not really that slow. It's pretty fast in comparison. It's faster definitely than nitrogen and oxygen. And carbon dioxide, remember, 44 grams per mole. So that's the slowpoke of these different gases that are compared. So you see the velocity is inversely proportional to the molar mass. So Ludwig Boltzmann actually studied the average energy distribution of oxygen at room temperature. And here we see that he lived from 1844 to 1906, which is connected to his suicidal death. It's an interesting historical story behind his fate, but that would go too far for this episode. But if you're interested, you can read about it. Looking at gas constants, remember we just noticed that we used a different numerical value for R because it was computed with different units for the STP conditions. For the ideal gas law of van der Waals, we usually use the liters atmosphere mole Kelvin value, which is 0.0821. Here it's 206, but you can round it. Then we have calorie per mole per Kelvin, which would be 1.987. Then we can also use the energy form, joules per mole per Kelvin. That would give us 8.3. And this is exactly equal to Newton meters over moles Kelvin. And if we substitute Newton, then it's kilogram meter over second square times meter would give us meter square over mole Kelvin. And this is the unit we preferred for the root mean square calculations. And here's another one which uses the SI constant, which is the Pascal, cubic meters over mole Kelvin. So you see it's another numerical value. And then we can also use liters torr mole Kelvin. So there are different values depending on what kind of units one is using. Remember, joule is the energy unit and can be substituted for Newton, which is force, and meter is the distance. Newton is defined as kilogram times meter over second square. Mass times acceleration, which is a force in physics. The calculation of molecular speeds, we can go through this very quickly. I already discussed that with you, but here we have it worked out. For instance, what is the speed of an oxygen molecule, or the average speed of all oxygen molecules at 25 degrees centigrade? Just plug in the values, and then it turns out to be 482 meters per second. Why don't you convert that into kilometers per hour or miles per hour to see if it would pass you on the freeway? Molecular speeds have a lot to do also with what we can do with gases. Remember, the gases are constantly whizzing about with real high speeds, and occasionally they collide, but they never get close enough. They sort of swerve by each other. And the idea is to get the molecules close enough together so that they can temporarily polarize each other. That means shift their electron density areas not into a evenly spread out area, but to distort it so that the charges are not completely concentric. So that means we have a negative end of the molecule and a positive end of the molecule. We call that a dipole, indicated by delta plus or delta minus, as I've shown you in the episode 3. And here again we have these curves, these isotherms, meaning these are all curves for the same temperature, PV relationships, for different gases. And these are the ideal gases, and these are the real gases, and you notice that they have this plateau. This is the region in which we can have the equilibrium between liquid and gas. On the left we have the liquid physical state, on the right the gaseous physical state. Notice that the ideal gases don't come into this region unless we lower the temperature enough and the pressure enough, or increase the pressure. So the the temperature pressure combination that leads to the liquefaction or condensation of a gas is called the critical temperature and the critical pressure. Now for this particular gas, it would be 647 K and 22.9 megapascals. This is for this particular example. Now you see what happens when we don't have the correct critical pressure or critical temperature. Anything above these values will not lead to a liquefaction, no matter how hard you try. So you have to at least be at the region of the critical temperature and pressure, or either below it or above the critical pressure, below the critical temperature or above the critical pressure. Remember, the velocity vectors are still very pronounced. That means when the particles bump into each other, those are elastic collisions. They do not linger enough to do each other the favor of polarization. However, when you start slowing them down, they bump into each other, they linger a little bit longer, but the pressure is still too weak to really polarize them. But when you also increase the pressure, then you got a double whammy, so to speak, and then boom, the vapors will slow down enough, or the gas molecules will slow down enough, and with the pressure exerted, it's just too much for them, and then boom, you get the liquid. So that's very interesting concerning liquefaction or condensation of gases, the critical pressure and temperature. Now we are moving on to Graham's law, which makes use of molecular speeds. And Graham was a British scientist, lived from 1805 to 1869, and the scientist worked in many fields, so they didn't have that specialty area as much as today. But Graham, besides doing other things, did a lot of work on the effusion and diffusion of gases. So in a way, effusion means we have here two containers with a valve separating them, and when you open the valve, the gas naturally will enter the vacuum space until we have an equilibrium in concentration, pressure, left and right of this setup. So here we talk about diffusion or effusion rates is proportional to the square root of 1 over density of the gas. Remember, density is mass per volume. The volume is constant. So again, it's actually mass, just like we talked about in the RMS rule. Diffusion means mutual penetration of gases. So they pretend as if there's a vacuum on the other side. It doesn't make that much difference whether there's a gas in there or not. Remember, the density is so low of gases anyway. So they will also make sure that they occupy each side of the container with equal concentration. So diffusion can compare two gases. So we have the rate A over rate B equals the square root of the density or mass of B, so inverse relationship, over square root of the density of A in the bottom, or mass A on the bottom, or denominator if you would be more exact. So the effusion or diffusion rate is inversely proportional to the square root of the density or molecular mass or molar mass of the gas. And this can be derived by looking at the kinetic energy. So we have 1/2 mass times velocity squared is kinetic energy. You compare the two. The 1/2 cancels out. And if you put the volumes on one side and the masses on one side, we get this relationship. And if you take the square root, we get this relationship. So in the end, we come up with Graham's law. Here it is. So the average velocity of two gases is inverse to the square root of their molar masses, which makes sense. The heavier you are, the slower you are in your speed. So if we want to play a little game, who is faster? The big guy or the small guy? Naturally, the faster one will be the one that is less impaired by mass. So who's going to be faster, hydrogen or helium? You can say right now. Well, of course, hydrogen. This is how it works. Or let's just look at helium and oxygen. The velocity of helium over the velocity of oxygen is the square root of their molar masses. Inverse square root, or the square root of the inverse relationship of their molar masses. So you see oxygen is here, 32, and helium is here, 4, and that is the square root of 8, and that's 2.8 over 1. So that means, if you cross-correlate, helium is 2.8 times as fast as oxygen, almost 3 times as fast. Next, we would like to talk about Dalton's law. Dalton also, as you know, did various things, but he certainly also considered the study of partial pressures. Considering the kinetic molecular theory, let's say we have a pressure over the liquid here, the interface is right here. So let's say we have different gases bombarding into the surface or the container walls, then we can say the total pressure is the sum of the individual pressures, because all the gas particles will have a collective effect. So we can say the total pressure is the sum of the partial pressures. This is very important in calculating the real pressure of a gas. When we collect it over water, for instance, then of course water molecules will also be in that gas component. And if we want to get rid of the vapor pressure, then we just have to take the total pressure that we measure, and we can look up the vapor pressure at certain temperatures, and then just subtract the vapor pressure from the total pressure, and then we get the pressure of the so-called dry gas, and dry gas means no water vapor contamination. Gases are usually collected in the lab by the so-called downward displacement method. We have a pneumatic trough, which is just a bucket with water. The bottles are inverted into this liquid and first completely filled with water, and the gas that is produced will push down the water level until it's completely filled this bottle. And then you have to fish out the bottle, making sure that no gas can escape, and then we have the gas trapped inside. So this is a very good way of collecting gases in the laboratory, because otherwise the gas would escape. An interesting thing about different gases, they have different densities and different molecular speeds. There is a case which is the Dogs Grotto in Naples. It's known for the fact that all the dogs die but the humans survive. Good question, why is that happening? Well, the dogs have their nose closer to the ground, and the cave has a lot of carbon dioxide and it settles more to the bottom. The air is more on the top. So we have a layering effect here. Carbon dioxide being much more dense than than air, and therefore even any low life animal, so to speak, meaning having a nose pretty low, will succumb. Now don't take your babies in there in the carriage, it has the same effect. So the density of carbon dioxide is larger than air. So the fellow here is singing a sad song. The hot air balloon is also based on different densities. Hot air is less dense than cold air. So you remember you have to make a little fire here to get the air inside of the balloon warmed up, and then you can have some interesting travel around the world in 80 days, if you like. Here you have some numbers for the gas densities. You see air is 1.78, carbon dioxide is 1.96, so you see it's much more dense. Chlorine gas is really dense, and here we see hydrogen definitely being the lowest. Carbon monoxide wouldn't be so much of a problem, it's 1.25. Here we would like to look at an application of Graham's law. For instance, in order to get enough fissionable uranium, you convert these uranium isotopes into fluorides. And look, they have different masses, right? One is 235 uranium hexafluoride, and one is 238 uranium hexafluoride. Guess which one is going to be slower? Of course, the heavier one. So they can do, by virtue of diffusion separation, one can amplify the 235 fissionable uranium hexafluoride and isolate it and separate it from the heavier uranium hexafluoride. And that is the one that is needed for making bombs. So that's called isotopic enrichment. So that's used today. Before we close with the gases, let's look at some interesting things which we call vapors. Vapors are actually gaseous forms of molecules, like water vapor. So iodine goes directly from the solid into the vapor phase. Nitric acid decomposes into nitrogen dioxide, and you get always the brown vapor on top of the liquid. And we know about water vapor, and we know about aromas of excellent wines. So vapors are gaseous forms of liquids. Here we have an example of how certain molecules that are in our cosmetics can have an effect on dogs, for instance, because of methylparaben, which is a sexual attractant pheromone. So that's why be careful when you put on your lotions that no dog is in heat. So it's found in the vaginal secretions of female dogs in estrus. And you can look up this article if you want, Science 203, page 559. It was published in 1979. But look at your cosmetics and lotions. It usually contains methylparaben as a preservative. And last not least, let's look at how gases are transported. They are transported in compressed cylinders that resist the pressure, because they're under a tremendous pressure in these cylinders, so they have to be of a thick-walled steel. There's a color code for the cylinders, and I don't have them all here, but green is usually oxygen. Helium is usually gray. Depending if it's oil-free, it has a yellow-brown top. Helium oil pumped, there's a red ring around it, and so forth and so on. Acetylene is yellow. Carbon dioxide for fire retardant work is red. Normal CO2 is usually gray. And we have blue bottles and so forth. So it's just interesting to say, when you go around and in your life, see if you can see these compressed gas containers. Many restaurants have them, your dentist has them, and so forth. And check out the color, and you can learn already, that gas is nitrogen, or that gas is CO2. Thank you. Goodbye.